So my name is Kevin Holbrook from CADimensions, and this is a presentation focusing on how flow simulation can embed itself in your design process to allow you to innovate a little better and make design decisions much sooner in the cycle before you get to any of that physical testing. A couple of questions or polls for you this morning, just to get a sense of the group that we have online and the types of things that you're doing. First of all, do you ever do physical testing to optimize the flow on your products? If you could just answer here, and we'll use some of this information during our presentation. Okay, I'm going to go ahead and close and show you the numbers here. So it looks like a lot of you are doing physical testing. Since you're doing physical testing, what is the average number of prototypes that you're creating to be able to test various scenarios which require flow? Go ahead, if you wouldn't mind voting here. Now the answer to this question is the reason why we're here today. Let me go ahead and close the poll, and I'll provide you the numbers here. It's very costly to create prototypes and to physically test for flow scenarios within or around your products. Whether you have to rent a wind tunnel or set up some expensive internal flow testing, it costs some money to do so. Now my final question is for those of you who don't do physical testing, or even those who have you ever outsourced any fluid flow simulation? If so, think of the costs related to being able to do that. Again, that all factors into our conversation today. And just to give you an idea here, here's what we're looking at. Half have not. So we're pretty even here. So let's go ahead and get started on our presentation today. What I wanted to cover just real briefly before we get into the software, talk a little bit about the product development processes that exist today, what is and how does design simulation kind of fit into that. More specifically, the flow simulation application. Hopefully most of you will be attending this afternoon's webinar that's specific to a couple modules that are a part of the flow product lineup. And then we'll get into the demonstration and kind of summarize what we've discussed today. So most of you have been around SOLIDWORKS products for a while, have seen this slide. Oh, let me go back here. The typical product development process that you detail your product and then you validate it through physical testing, and then any changes you need to make has to come back. But what I want you to consider and think about in your own organizations is how often you innovate and develop future products based on new innovations. Do you have the time to be able to do that type of thing early enough in the process to make those proper decisions? And what we're seeing is a lot of times, innovation is what gets cut out of the cycle because they don't have time to really look at the consequences of doing something that's different. There's risk involved in making those decisions, and the innovation kind of gets cut out to what we've always been doing. So with all of SOLIDWORKS products, this is what we always propose. This whole idea that we're able to simulate our products during the design cycle. While I'm designing, I can look at different scenarios, look at different changes, and that's what I'm going to show you with the demonstration today. And not only does that allow you to move your cycle times a little bit earlier, but it gives you time to innovate on your products. Okay. Now, what is design simulation? I mean, this is terminology that that the SOLIDWORKS family uses. It really just has to do with predicting performance while you're designing. Okay, not waiting till you've completely designed and released the product that you're working on. It's during the design phase. Okay, we can perform these types of simulations with other products like structural and motion, and today we're going to talk fluid flow and heat flow, environmental impacts. All of those things can be done as design simulation concurrent with your design. So what is flow simulation? Okay, it's an integrated tool for fluid flow and heat transfer directly in your SOLIDWORKS 3D CAD. Okay, it's true concurrent engineering. So if I'm a designer and I'm starting to develop a new valve and I'm looking at the internals and the angles and radiuses inside, I can truly take a look at what's going on. Now it will handle internal and external flows, laminar, turbulent, and transitional, rotational parts, compressible and incompressible fluids, Newtonian and non-Newtonian like blood and honey. We're going to show a heat transfer problem today as well. You can do gas mixtures, liquid mixtures, heat transfer in solids, water vapor with steam, subsonic, transonic, and supersonic flow, time-dependent flow. So there's a lot of different areas that this product could fit into your design cycle. Now, some of the engineering challenges that you're able to solve using this tool, one of the examples that I'm going to look at today is how do we calculate pressure drop within a system. You know, looking at the flow fields and truly understanding how the fluid is going to flow within or around your products. Once you have that understanding, you can make geometry changes to optimize that flow to make your products better. Whenever you're dealing with thermal phenomena, how do we transfer heat throughout the system? Whether it's an electronic box with some sort of electronic circuits inside, or other scenarios where you have hot fluids and gases running through. How do we handle that energy and work with it? And then how about something else, force prediction? One of the examples I'm going to show today, we want to look at how the forces as a result of the flow are affecting the individual components. Well, we have to consider that, right? It's not just how it's flowing through. How is it affecting the materials based upon the forces of the flow? So let's go ahead and jump into the product, and we'll come back in a little bit for a summary. So part of the message today is the fact that flow simulation is a concurrent design tool. Now, in order to be a truly concurrent design tool, it must be seamless. It must run inside of SOLIDWORKS. It must be able to recognize geometry changes inside of the CAD tool so that I can make those decisions up front. So first thing is the software gets turned on inside of SOLIDWORKS as an add-in. Once you turn on the add-in, you end up with another tab in your command manager and another pull-down menu. Now, my first job from a CAD perspective is to determine whether I'm dealing with internal or external flow. In this particular case, all the flow is internalized into this globe valve that I have here. And I want to be able to analyze it in multiple positions. So what I've done is I've created configurations where it's fully open, fully closed, half open, 3/4 open, so I can get a sense as to the different positions and how those might affect it. Now, in order for the software to figure out where the fluid actually is, I need to provide it with an enclosed area inside this pipe, inside the valve itself. When I'm dealing with that, well, obviously the ends are open, so I'm going to have to do something to close those ends. Now, there's tools within the software to tell you, hey, show me if there's a fluid volume. Okay, and it can go through and find out if there's a fluid volume, a proper fluid volume within it. Now what I need to do in this case is I need to close off the fluid volume so that the software can figure out exactly where I'm going to analyze the flow. Now this is simple in SOLIDWORKS because it's inside the CAD tool. I can open a sketch, insert a part, extrude a cap on there, or with Flow there's actually a tool that will allow you to create lids just by making selections on surfaces. Okay, so I'm going to select the cylindrical surfaces, and the result is the software is going to go ahead and create a couple lids that are going to close in that volume. Now when I do that check geometry and I tell it to go ahead and show the fluid volume now, it's able to understand the internal structure and see that it's completely watertight. Now what you may have to be concerned with is gaps between components. You want to make sure there are no gaps, so you'll model them so they're touching. But what your goal is to get that internal flow volume so you can go ahead and solve this problem. So setting up a problem with Flow is very simple because we have a wizard-based structure for setting that up. And this is how I start all problems. So go ahead and launch the wizard. And what it does is it takes you step by step to set up the problem, giving all the inputs and setup requirements. Now it also ties to SOLIDWORKS configurations. So I can use a current configuration, or I can create a new configuration using this tool as well. I can give this a project name. We'll call this GV1. And any comments that I might use later on, and just kind of work my way through the wizard system for setup. Now when it comes to units, there's some predefined unit systems. All the units are managed in something we call the engineering database. The engineering database contains things like my units, my materials, any fans, any default data that I would reuse from problem to problem would be stored in these types of systems. Now what's neat about the unit systems, when we're looking at the units that we're using, let's say in this case for pressure and stress under the SI predefined system, I can actually modify and select any of the units I want to use for a particular parameter, for a particular characteristic. Once I have that, I can actually create a custom unit system like I did here. I have a unit system for my globe valve. I can go ahead and select that from the system and move on. Now here's where we start to look at the different analysis type and phenomena within the analysis. Is it internal or external flow, or is it both? Do I have fluid flowing on the outside and on the inside? Okay, in this case it's just internal. One of the ones I'm going to show you later on is heat conduction in solids, actually transferring thermal energy between components. Are we dealing with radiation? Do we want to see what the flow looks like over time at 100 seconds and 500 seconds and 1,000 seconds? Is gravity playing a role if you're designing or optimizing heat sinks and how you're mounting the heat sinks and the number of fins? You can actually show as if it's mounted and what the gravitational effects are on the thermal energy being released. And then rotating frames are options as well. Again, the wizard, we just kind of work our way through. What fluid is actually running through the system? This is all coming from the engineering database, gases and liquids, and I can go ahead and select what I want in here. Okay, in this case it could be air. Let's go with water. Throw some water in here, and there we go. Now some default parameters for wall conditions. We're going to leave that. One of the things when you're doing a flow simulation that's beneficial is if you can give parameters or initial conditions that are close to where you expect the final result to be, it's going to solve the problem a little bit quicker. Now in this case, I have no idea what's going on inside the system, so I can't really change any initial parameters to accommodate that. If you've used any of our other simulation tools in the past, it uses a concept called meshing, where it actually takes the fluid volume and breaks it down into solvable mathematical pieces. There's tools built in here to automate that process, also to automate the inspection and finding of minimum gaps and minimum wall thicknesses. If you develop baffles and those types of things, it will understand that. Now this is the last screen. Once I've provided it the information, it's went ahead and it's created a flow simulation tree which lists any projects that I'm currently working on within flow simulation. On the bottom is the actual project itself, and all the individual inputs and any results are going to be worked on from there as well. You'll notice that I have now several commands within the system that I can work with on my command manager. If I decide I want to customize SOLIDWORKS, I do have the ability to add any of the flow commands directly to my toolbars, to my mouse gestures, to hotkeys, so it's completely integrated into your design cycle. Okay. Now, in this case, what I need to do is set up the actual flow parameters or boundary conditions within the system. We'll just do a cross-section so we can get a better look here. So first of all, my boundary conditions, everything is kind of done from a tree. There is icons that you can use for this, but I can insert a boundary condition, and I have some choices here. Is it a flow opening, a pressure opening, or is it a wall? For flow openings, you can have inlet mass flow, outlet mass flow, volumetric flow, velocities that you can apply. In this case, what we're going to do is apply a inlet mass flow rate of, in this case, it's going to be 0.6 kilograms per second of flow rate. Okay. Now notice I'm picking the inside surfaces of the caps, so I'm actually applying that condition incoming to the system. On the other end, my boundary condition can be set to the other surface on the lid on the other side, and this is just going to be a pressure opening to environmental pressure. Now we can also specify the temperatures, and this doesn't happen to be a thermal problem, but the temperatures of the fluid coming in or at the exit, we can specify that at any point as well. Now that box that you see in the graphics area is the area in which it's solving. It's not necessarily the fluid, but the area that it's breaking up to solve for the flow. We call it the computational domain. Now we really have everything set up that we need to solve the problem. However, I want to help the system come to the solution that I require. And in order to do so, it's best for me to apply what we call goals. And there's different ways of applying goals. Global for the entire system. Maybe there's a specific point within the system that you're worried about, or surfaces. Okay, in this case, let's apply a couple goals. For my global goals, you can see that there's all sorts of things that we can use in here. We want the average velocity, and I can leave it in here so that the software uses this to complete the math on the problem. It's used for convergence. Okay. And then I also have some surface goals, because one of the things in the system that I want to find out is what is the pressure drop. So if I select an individual surface, okay, I can tell it my goal for that surface is pressure. Okay, go tell the average pressure, and then we'll do the same thing on the surface goals for the other side, so we can figure out what the pressure is going to be on each side. Now you can also use these to create equation goals. So what is the pressure drop? Well, the pressure drop is this, which is my pressure at the inlet, minus this, which is my pressure at the outlet. So goals are important just to help you get to the proper answer as quick as possible. Now, we're ready to go ahead and run this. Now, this one doesn't take very long to run at all, but what I want to show you here is the solver window. When I first started using this product, one of the things that helped me so much learning and understanding what's going on is the solver window. Because once it prepares the model and meshes and gets it ready to go, I can get results in real time. So at each iteration that it solves, I'm able to go ahead and view what those results look like. In this case, let's go ahead and plot out velocity in a cross-section. So as each iteration finishes, I get a good idea as to what that flow pattern looks like across a cross-section. And with all the goals that I've applied, that I've told the system, you know what, stop when you've converged on these particular goals, I'm able to get my results based upon convergence on what I'm looking for. Now the solver window, this one ran real fast, but you do also have the ability to suspend or pause the solving. You can also batch run, set up a bunch of problems and run them overnight. You can clone or copy studies and run them on multiple configurations. So if you're not sure how you want to design something, you can create multiple configurations and run against that. I'm going to go ahead and close this for a second, and we're going to use one that I ran ahead of time that has a little more mesh and multiple projects tied to it. So let's go to our fully open project and take a look at what we can do once we have the results. Now, first thing I might want to do is to get a better visualization is kind of set it transparent. Once I have the results, we can kind of work down this results tree to look at the results of the problem. Now, first thing is a cut plot. Now, if I look at a cut plot, what that allows me to do is display different things like the mesh and the contours, but display like velocity across a cross-section of the model. Now, I can get an idea using the chart here about what my velocity looks like as this thing is fully open, where the velocity increases. You can see I kind of have some dead spots as the flow makes its way up and around the valve. You can see also in here there's some dead spots. So it gives me a better understanding of what the flow looks like. Now, these cut plots can also be animated. If I select play, the software is going to automatically start to drag that cut plane forwards and backwards through the flow region, so you can get an idea if there's any variation in that, call it the Z direction in this case. Okay, these can also be saved out as videos, as images that can be used in reports later on. Now, you can have as many cut plots as you like, so I can insert another one. Maybe I want to look at the pressure distribution along that plane. I can look how pressure is increased and decreased throughout the system as well. Okay, and these all can be used later on. Let's say I wanted to plot out one of these parameters on a surface or surfaces. In this case, I'm going to use all the faces of the flow region, and I want to plot out pressure on all those faces. So I almost get a three-dimensional look. If I rotate this thing around, and I apologize on the webinar, I get kind of a 3D look of all the exterior faces and what's happening relative to pressure. At any point in time, I can go ahead and edit any of these plots, maybe change a parameter. Let's look at velocity instead. I can go ahead and take a look at the velocities, okay, at the wall. Now, next one I want to show is called flow trajectories. Now, a flow trajectory allows me to use any of the areas where fluid is entering or exiting the system to tell the software we're going to insert a massless particle, and we want to see where that massless particle goes. In this case, I'm going to use 60 points of arrows coming in the inlet, which is the face to my right, and it's going to actually show me, zoom in here a little bit, using arrows what that's going to look like. Now, that does help me visualizing a little bit of the flow and how it gets around this center plunger. But what I'm able to do also is play these. So I can, and hopefully this comes across pretty well in the webinar, but you can actually animate and see these massless particles flowing through your system. So you talk about really understanding your flow region. Well, this gives you a fantastic tool to do that. And again, you can save out videos and do other things along with it. Now, one of the things we set out to do is to find out what the pressure at the inlet, pressure at the outlet, and what the pressure drop happens to be. Now, I can go ahead and insert a plot that plots out each of those values. So I can select any of my goals. I can tell the software, go ahead and show me what I'm looking at. So my velocities and my pressures, inlet and outlet, and then I can tell the system, let's set up pressure drop here. So here's my pressure drop with the change in pressure from inlet and outlet. Now, the great thing about all this information that we plot out, whether it be on a particular surface, a point, it has such a tie to Excel. I actually can say export to Excel, and it's going to launch my Excel. It's going to give me a nice little chart showing me all the parameters that I've just specified, but it's also going to plot it out over time. So looking at my velocity over time, my inlet pressure, my outlet pressure, and how that varied in my pressure drop. On top of that, all the data that we just asked for is thrown into Excel and can be used in other programs. Okay, so its tie to Excel is phenomenal. Now, the same thing goes for reporting. When I decide to create a report, I have tools within the system that allow me to create and modify templates. I can go ahead and add pictures, videos directly to this. And let's pick a template here. Okay, so the formatting of this is completely up to you, but it gives you all your parameters and setup parameters, all your results, and if I added any videos or images, those will also show up. Again, tied directly to Word, allowing you to create nice little templates and kind of work with it from there. Now, since I did configurations on this, I can take a look at, what if this thing was only opened a little bit? Okay, you'll see my plunger kind of move down a little bit. Well, now I can load those results if I ran them and show cut plots on those. You can see the increase in velocities because of the valve being partially open. Look at the differences in the flow patterns. I can do my flow trajectories and show those. So, my message in all of this is I'm in SolidWorks. I'm in the design tool where I don't have to, wait for somebody else to give me an answer. I can go ahead and now make a change. What if I change the radius on this casting? Okay, what if I change the angle or direction of the flow tube coming in? Again, we talk about innovation and optimizing your products. This allows you to do it real time. Okay? So another example I want to show you. This one's going to be a little bit different. But we're going to take advantage a little bit more of what SolidWorks has to offer in this case. So let's just do a little bit transparent here so you can kind of get an idea. What we have is a piston valve. And we want to take a look at, let's go here. We want to take a look at the forces on a particular component within the flow region. We have a pressure drop, a given pressure drop, a difference of 1 bar between the two, and that's going to result in some sort of flow rate through this valve. And that's going to, the flow is going to come in contact with this piston in here. So how did I set up a problem like that? Well, I went through the wizard, the same as what I just showed you. My conditions on this are very simple. I have a lid that's set to a 2 bars of environmental pressure on the lid there. And then I have another lid, which this one's kind of neat. It's just a solid wrapped all the way around the outside. Even though there's only a couple holes, I can apply a 1 bar parameter to that. But when it comes to goals for this problem, I want to find out what the mass flow rate of the system ends up being. But more importantly, I want to find out what the force is like in the x direction on these surfaces within the system. Now when this gets run, I'll go ahead and load this. You're going to be able to do the same things we did on the previous study, plotting out cut plots. Go ahead and show that. There's a cut plot with pressure throughout the system. You can do your flow trajectories to take a look at how things are flowing inside. Zoom in a little bit here and animate this. Okay, get an idea. I can do my goal plot where I can look at what the actual force on those surfaces happen to be. And I have a force of 2.3 newtons on the surface of that valve. So what I want to do here is I want to optimize the force at around 1.8 newtons. I want to see what position this piston has to be in to get my 1.8 newtons of force that I require. So here's how I might do that with flow simulation. Flow simulation gives you the ability to create what we call a parametric study. After all, we're in the design tool, right? What if I want to change parameters of the CAD and see how that affects the flow? That's what we're talking about, right? So in this case, I can set up variations. Okay, let's just get rid of this one for a moment. So I want to add a parameter in here, and we're going to vary, in this case, a mate. So I'm going to vary this mate of the piston. Now how am I going to vary that? Well, I can give it an upper and lower limit. So I can say here's my mate distance, and it happens to be in meters because that's the units of my study. It can go between these two, and my steps are going to be every one. Okay, so it sets up, all the different steps that I'm going to solve for. And then I tell it what my output parameters are. I'm going to actually modify this a little bit. Remove, put one more 0 in there than I wanted. Okay, so we're going to do 3 steps. Now for my output parameter, I want to grab the force data, the resulting force data once it changes that. And then here's the scenarios that I'm dealing with. Okay. Now, once I have all these scenarios in here, I can run these, and the software is going to modify the dimensional value, and it's going to solve for each scenario as I run. Notice I get real-time results here. Okay, I can take a look at how the velocities are affected as this thing is solving, how many iterations as it completes, and you can see the piston just moved again. In that first position, I don't know if you caught that as it flipped through, it was about 1.7 newtons of resulting force, and I can continue to optimize my design, optimize position of components, optimize geometry using flow in your flow solvers. Okay, I'll let this go ahead and complete, and then we'll move on to our last example problem and close it up for the day. All right, so if we look at our results here, you can see at the different mate dimensions, this one's close to the 1.8 Newton force that I wanted to have. So now I can play essentially with the mate in a certain range to get a solution. But isn't it great to be able to use your SolidWorks or your CAD system to help you to optimize using dimensions or positions of components? Now the last problem I want to show really helps us to segue into this afternoon session. There are two add-on modules for flow simulation. One that is very specific for circuits and thermal energy from circuit boards, printed circuit boards within a system, that allow you to specify the chip-to-board connections and all the layers in the boards, and has some specialized tools for that type of thing. Well, in my particular problem, I'm not really concerned with the board and the temperature of the board. I'm really looking to get an idea of the overall airflow inside this system. So I have an aluminum heatsink, some capacitors, a power supply. I have a bunch of chips mounted to a mock board over here, and there's a large chip underneath the heatsink. Now, I set up this problem the exact same way. I'll go ahead and kind of work my way through this, and then we'll come back to this one. Okay, give it a project name, tie it to a configuration, just like we did before. Select my units that we're going to use. Select the type of flow. This is internal flow, but I'm also dealing with heat conductions in solids. I can also deal with gravity in this case because we're dealing with thermal energy and how it might rise within the system, and I can tell it what direction gravity is. Is it time dependent? Not in this case. Okay, what fluids? In this case, we're dealing directly with air. Now, because we're dealing with heat conduction in solids, we also have to supply the system with a default solid. So maybe everything is some sort of aluminum alloy. I'll just stainless here. As a default, we can always override it. Again, setting our initial parameters, setting our result resolution, and we've went ahead and set up a particular problem. Now, from here, I'm not going to go through all this, but what we need to do is now apply the proper materials to all the components within the system. Now, if I select things like my main chip, I can go ahead and go to predefined materials. This is all coming from the database, or I can go to a particular problem and find the material. Okay, so we go through this process with all the components, making sure material is defined. The next thing in this case would be my heat sources. Well, I might have a volume source on a component. Let me select another component here. We'll do the heat sink. Sorry, let's clear that. We want the chip. The main chip, and what is the wattage on the main chip? In this case, 5 watts. We can define that with heat generation rate or volumetric generation rate or an individual temperature. Okay, so I go through and do this 5 watts on the chips here, 4 watts on the chips here. The capacitors are going to be at 100-degree temperature, and the power supply is going to be at 120. Now you'll notice that I have lids for the inlet and the outlet, but the inlet is actually going to be a fan. Now we can go ahead and define fans as well. What I can do is insert a fan into that inside surface. Okay. Now we have predefined fan curves that are part of the system, again in the database, where I can break down by manufacturer, AC or DC fans, full speed, and select actual fan curve data that's stored in here. Or I can create my own fan curve and be able to make a selection as well. I can give the temperature of the fluid coming in at that location. So now I can simulate an external internal fan blowing air within the system across the heatsink. Now for the outlets, just like we did before, we're going to give it a pressure opening to environmental pressure on the inside surface of all those outlet components. I'm going to switch to the completed one here so you can kind of see everything's all set up. My main chip at 5 watts, my caps at 100, my small chips at 4, my power supply at 120. Well, let's go ahead and load these results. Again, we're not getting down to the level of the circuit board and the circuit board design, but looking at the overall thermal imaging of an entire system that has electrical components in it is important. So, cut plots. Here's a cut plot showing temperature throughout the system. This is a great one to animate and play. You can see in between the boards that the temperature is up there a little bit as you get down to the chips. You know, we're not really cooling these very well. Okay, let's go ahead and do a surface plot. In this case, I want to plot out the temperature of all the solids in the system. Let's plot that out and hide our initial. So here's the temperature values for each of the chips, the main chip and heatsink, the capacitors, and so on. But again, I can look at what that's going to look like. Now here's a great one to look at flow trajectories. We were going to look at using arrows and what the temperature is, or velocity. Let's use velocity throughout the system. Again, animating this is going to give you some real results as to what the flow patterns are going to look like within the system. Placing my fan where I have it, blowing across the heatsink, is definitely keeping the main chip cool, but I'm not getting enough air over to the other components on the boards to cool them properly as well. Okay, these are the types of things that you get with a flow simulation product. Okay, so to close this out, let's go back to my PowerPoint for a moment. What we're talking about today with flow simulation, hopefully you got from this, is the fact that the folks in your organization that are doing the design are going to be able to use this as you're making your designs, as you're trying to figure out which geometry is best. It's embedded in SOLIDWORKS so you can perform those operations right then and there. Okay, concurrent engineering changes how your products are developed. I mean, it changes that cycle considerably and allows you to innovate, create better products, and not to mention to validate your product performance. Now, for those of you who said you create 2 to 5 or 10 plus prototypes, wouldn't it be nice to simulate at one time using flow simulation and then do one physical test on the final product to validate your results? Okay, think of the cost savings by creating less prototypes and how that can help you to get this software in-house and have it make a difference immediately. So a little bit about what other customers are saying about flow simulation. We have a lot of customers using this product in upstate New York and all over the world for that matter. You know, it really comes down to validation and innovating within your product. Here's a couple examples. Okay, a couple more here. Dresser Inc. Didn't have much insight as to what was happening inside the pressure vessels. This gives an exact idea of what is truly going on within their systems. IO save $15,000 on product development by using this particular tool. So I want to thank everyone for coming out today.